Hello everyone, I am Kshitij and today we will be exploring laws of motion, right? It is a very important topic to explore when we are talking about competitive exams such as NEET and JEE, right? This is of paramount importance when we think about classical mechanics, right? Because it was a defining moment in the history of physics, okay? So we will start with talking about Isaac Newton, okay? Then we will talk about frame of reference, followed by what is force, right? Types of forces and pseudo force, okay? When we will be talking about force, I'll just give a soft introduction, very soft, about what pseudo force is, because we will be needing to talk about it later, right? In a bit of detail, not that much but just a little bit, just so that you can understand what pseudo force is, right? Okay, after that we will be talking about momentum. Then we'll be talking about how it is conserved, right? The law of conservation of momentum. But in this case we will be just talking about linear momentum. So conservation of linear momentum, right? Then we will start with the laws of motion, right? First we will talk about the first law. Then we'll talk about inertia and types of inertia, okay? Then we'll talk about second law. When we are done with talking about the second law, we will discuss the validity of the first law, right? The validity of the first law, and based on that we will talk about the types of frame of references, okay? Frames of references. I'll just put a small thing, it will take no much time to write a whole lot, and then we'll finally talk about the third law. And once we are done, you will basically understand that all of these laws and everything is basically connected, and they are kind of interpretations of each other, okay? So let's start with talking about Mr. Newton. So why are we talking about Mr. Newton? Okay, to put it appropriately, to be technically correct, and to show all the respect in the world to him, let's call him Sir Isaac Newton, okay? So why are we talking about Isaac Newton in the first place? He has had a lot of discoveries in physics, and he was the one who discovered these laws of motion. But before that, he found out the law of gravitation, the law of how the apple fell on his head and he made lives miserable for all of us. Yeah. Then he also he discovered differentiation, okay? Right now he discovered the law of gravitation in 1666, right? But it was in a publication, it was published much later on, right? In 1687, yeah. And differentiation, now this is a controversial thing. History also says that a German physicist, German scientist, German mathematician, he also worked on differentiation, integration, right? This is collectively called calculus. Now His name was Gottfried V. Leibniz. Gottfried V. Leibniz. Okay, not important in this case, but a nice fact to remember. Okay, nice fact. So he published his work in which he discovered calculus, right, and made lives easier and miserable for everyone. This work was published in 1684, right. Newton's first collective work, which carries all his observations, all his theories, all this work, most of his work, not all of his work. The name of it is quite complicated. I will write it just now, but this was published in 1687. Why am I mentioning the year? If you notice here, 1684 and 1687, he found out in 1684 what is calculus, how it works, and what Newton did was he had started writing his work much earlier, okay, because the law of gravitation is a part of that work, right? And in different parts of this publication, he has used different forms of calculus to discuss different phenomena. The name of this work is Principalis, not Principalis, Philosophiae Naturalis, Philosophiae note this A and E are together. Philosophiae Naturalis Principia Mathematica, right? This was one of his important works. This was published in 1687, and some of his calculus related work was also in another publication of his, Optics. We are not going to discuss that, just to mention this, right? So in this Philosophiae Naturalis Principia Mathematica, he has mentioned the law of gravitation, he has worked on calculus, and why I have mentioned this is he has worked on the laws of motion. Okay, now this was originally published in a different language, not in English, even though Isaac Newton, I think he was an English physicist. So it was published in Neo-Latin before, right? Some people refer it to as the classic language of the sciences. Now, the meaning of this name, if you think about it, it's not very hard to understand. It's the mathematical principles of natural philosophy, right? Okay, so if you can see, calculus here, this is earlier, but this is later, right? This was discovered later on that he worked on it, in 1684. That's why we have Gottfried V. Newton. Okay. So before we talk about the laws of motion, we have talked about Newton. I hope this much is understood. These were just facts. They are not important per se for clearing your exams, just a nice juicy bit of information, right? Okay, so when we talk about laws of motion, there is an important word called law. What is a law? Think about it. What is a law? So is it something that is universally true? Is it? Think about it for a second. Is it? Maybe, maybe not. So why are these necessary? So if you think about things, right, we do massive derivations, we have different calculations, so it's not possible to move forward if we are stuck on doing the same thing again and again. So we put in a law, right, which is used to further research, to get to advance more in science, right? So we can define a law based on 4 things: 1, 2, 3 and 4. First one, it's concise. Okay, concise. So what do you mean by concise? It just means it's explained in a short manner but very clearly, right? So instead of explaining everything, all the derivation and everything, you can just give a plain statement, but it has all the important details in that statement. So that's what it makes it concise, right? Second, universally accepted statement. The key word is accepted, not true, accepted. What that means is it's true till something else, something better makes it untrue or refines it or makes it better, right? So that's why it's universally accepted. It's based on patterns or regularities in nature. No, you can say it describes patterns and regularity in nature. The difference between pattern and regularity is very small. It's just that if you have one pattern, it's isolated by itself, you're describing that, then you are giving the definition of a law which just describes one pattern. If you are describing using a law which describes a regularity, so that regularity will be a combination of different patterns. That's all. Okay. And the last and most important thing, it is based on repeated experimental evidence. Based on repeated experimental evidence. Now, why is this important? Why did I mention the law of gravitation? So based on experimental evidence, these laws can change. So when we discovered gravitational waves, right, the law of gravitation was rendered obsolete. Why? Because the gravitational waves, they kind of described that gravitation is not instantaneous, but the law of gravitation by Newton, it kind of describes gravitation as something which is instantaneous, right? This was one very important factor. That is why when new experimental evidence arrives, right, then this description of this pattern or regularity will change. The statement will be accepted in a different manner universally, but the only thing which remains true in all the four of these always is that it's concise. Okay, even though a law might be disregarded later on, the one thing which will remain is that it's concise. Okay, so that's what a law is. What is motion? This must be the simplest thing to explain in this lecture. So imagine you are sitting right here. Okay, you are sitting right here and you are observing something move. Okay, something is moving and you have a clock with you. Okay, now with this clock you can measure how the position of that object changes, right? But there is one very important factor, that those are the surroundings. Why? Because there's no such thing as absolute motion. Motion is always relative, right? So if you are sitting here, you are not moving, right? But this is a very key thing to understand. The earth is moving and you are on earth, right? So you are also moving. But in that moment when you are looking at something and thinking about whether it's moving or not, your frame of reference changes, right? So am I looking at something moving, or am I being looked at which is actually moving, right? That's the question. Very key thing which makes these things unambiguous, right? removes the confusion, right? So for example, if you are sitting in a car, okay, I am making things simpler, right? I am not very good at drawing, okay? So if you are sitting in a car, right, and there is someone sitting here outside, okay, if he is looking at you, to him you are moving, but to yourself, you are sitting in that car, you are at rest. So that's why that frame of reference, these surroundings, they become important. So what is motion? Now it is the change in position, right, as time passes with respect to surroundings, with respect to surroundings. Now if anything by chance gets missed, you're not writing with me, you can just rewind and pause and write it again, okay? So this is what motion is. So those laws which were discovered by Newton, which describe motion, right, they are called the laws of motion, okay? So we have understood what the title means. Now what is a frame of reference? As I mentioned before, there was this dude, he was sitting right here, okay? He is observing this object that's moving, right? So the frame of reference, it is a coordinate system attached to the observer, okay, who can observe the change in position, right, and he can also observe the time passing, okay? That is the frame of reference. I hope you have understood what the frame of reference is. I'll just give another example if you want. So imagine if you are in a train, right, and that train is moving, okay, that train is moving. So you are sitting inside. For you, you are at rest, right? Your frame of reference is yourself and the train. So to you, the train is stationary. It might be moving, but for you it's stationary. But if someone is watching from outside, the train is moving as well as you. So his frame of reference is himself, right? As he is looking at the train and he is looking at you. Please be aware of stalkers. Okay, so that is a very nice example of what is frame of reference. As we have given the example of a train, just think about it for 1 second. You are in the train, right, and you are sitting. A robber comes up to you and says, don't move. But you are actually moving. So that's why motion is relative, okay? So let's talk about what a force is. Imagine this object, right? It's right here. So if I am pushing this object, right, I am applying a force, right? Even if I am pulling this object, I am applying a force. So in doing so, I am applying an effort which is external, right? So force, it is an effort that pushes or pulls an object, and it changes its state of motion. It may or may not change its state of motion, okay? State of motion. and one more thing, state of motion or its direction. Okay, so that is what a force is. So what okay, so you understood that moving that object we are applying a force. What if we are applying a force and the object is not moving, right? So I am applying a force on this wall, but it's not moving. So that's why it's not necessary that when a force is applied, when an effort is applied, that object will move, right? So in that case we talk about that, right? The most basic formula for force is equal to mass multiplied by acceleration. Okay, m is the mass, a is the acceleration. Okay, just put a pin in that for a moment, you know, just think about it for a moment. We will be discussing how this formula comes, right? Okay, so when we talk about force, there are different types of forces in nature. The most basic thing that is important for foundation people, you know, like from 6th standard to 10th standard, there are only two types of forces, balanced and unbalanced. So I mentioned a force is something that may or may not change its state of motion or direction, right? So if a force is changing the state of motion or direction, right, it is an unbalanced force. But if it's not changing that state, it is a balanced force. That's all. That's how you understand what balanced or unbalanced, right? Okay, this is one way to describe the types of forces. But when we talk about real life, we have four main kinds of forces. When I'm talking about, you know, competitive exams such as NEET and JEE. So there is the gravitational force, there is the electromagnetic force, there are nuclear forces, then there are the weak forces. Okay, so gravitational force is self-explanatory, though that force which is applied upon any object by gravity, right? Similarly, the electromagnetic forces, any force which is applied to an object by electric components or magnetic components. But there is a relation between both. So if an object is, if a charge is not moving basically, so that the force applied on it is electric. But if it's moving or other factors are there, then that force can be electromagnetic. In that case, you can call it a Lorentz force, because this phenomena was described by Lorentz. Okay. Talking about nuclear forces. So nuclear forces, they only work on the nucleus of an atom. Okay, they only apply on the proton and the neutron of an atom. It's to hold it together basically, right? Because of the it balances out the electromagnetic forces also acting on them. Why? Because if you notice in an atom, we have this nucleus and we have different electrons orbiting it, right? So electron is providing a negative force and not negative force, negative charge, which causes a force on the proton, right? So imagine this proton is there and this electron is there. There are forces between them, and if you if you know, negative and positive charges, they attract each other. So how is this atom maintaining its shape? It is because of these forces, these nuclear forces that act on the proton and neutron, right? So this is what nuclear forces are. When we talk about the weak forces, this is not a generalization, I will talk about something very specific. So there's something called neutrino and anti-neutrino, right? Now these weak forces, they prevent or control whether a proton stays a proton or whether the neutron stays a neutron, right? So there can be a transition between proton and neutron depending on these weak forces, right? These weak forces will hold the proton together in itself, right? So nuclear force, it controls the structure of the nucleus, right? But the weak force, it controls the structure of the subatomic particles, these protons and neutrons, right? So what will happen is, there is a form of decay called beta plus decay, and there is beta minus decay. Okay. So in beta plus decay, a proton will break down, right? And it will release an electron, a neutrino, and a neutron. Okay, three things, 1, 2 and 3. Three things, right? This is beta plus decay, okay? But that does not mean that a proton is made up of all these things. Why? Because when we talk about beta minus decay, right, what will happen? Neutron will break down and it will release positron, anti-neutrino, and a proton. Okay, so this positron is the positive counterpart of an electron. So like an electron, it will travel in an orbit around the atom, but it will have a positive charge, right? Okay, so these were the weak forces. We covered frame of reference, we covered force. Momentum. Momentum is very simple to explain because the definition of it is just the mass of a moving object multiplied by its velocity. Okay, moving is not necessary. Okay, mass of an object multiplied by its velocity. Okay, so very simply, P is equal to mv. Okay, now the momentum I have mentioned right now, this is linear momentum. Linear momentum. There is another kind of momentum called angular momentum. We will not talk about it in this class, maybe next time or another class. Okay, so this is what momentum is. What it does, we'll understand when we talk about the conservation of linear momentum. I'll just write down conservation. So imagine there is a very strong bodybuilder. Okay, he does not look strong, but he is, okay, very strong bodybuilder, very powerful. He's standing on the ground. Okay, and a very short and weak person comes in running and jumps on that bodybuilder. Okay, jumps on that bodybuilder, but instead of this person moving, this short person, he just gets repelled back. He bounces off. Okay. Now this is what you observed. What the conservation of linear momentum says is that in isolation, note it, in isolation, the total linear momentum of a system does not change. Okay. So these two objects, they constitute a system in this situation. Okay. So let us think that the mass of the strong bodybuilder is m1, right, and the velocity of him is v1, right. Similarly, mass of the short one is m2 and his velocity is v2. Now in this example we are talking about, I am assuming that as the short person is colliding with the stronger one, the collision is elastic and there is no energy loss. So it's a perfectly elastic collision. Okay. So the coefficient of restitution is 1. If you know about it, that's fine. If you don't, we will talk about it when we discuss collisions, right? Not right now, just to mention this, right, because it's important. Okay, so in that case, m1 v1 plus m2 v2, right? So this was the later velocity. Okay, the velocity right here. Earlier its velocity was u1 and the shorter one was u2, right? So m1 v1 is equal to m1 u1 plus m2 u2. Okay, this is what this principle is. Now if you look at this equation, you'll think that okay, this is 0, this is some velocity, right? But the person is bouncing back. This has not changed. The big object has not acquired a velocity. No. Why? It might be that because of some reason this object has moved, it has acquired a velocity, but because of his mass, right, the change in the velocity was very short-lived and unnoticeable to the naked eye. Okay, that's why you were not able to notice that change, because that person is huge compared to the short person, right? So therefore almost all of that momentum, it gets transferred to the short person. Okay, so what happens is there occurs a change in momentum. This is the key word, change in momentum. Now for the short person, the change in momentum is enough to show a noticeable change in the velocity of that object. But for the big one, the stronger one, that change is not enough. Okay, that's why the object gets moved but it's not noticeable. I hope you understood conservation of momentum and the concept of momentum through this. Okay, now that we have understood this, let's move on to the first law of motion. It is also known as law of inertia. What is inertia? Inertia is the tendency of an object to resist a change in its state of motion, its direction, or of rest, right? So that is what inertia is. Inertia resists change in state of motion, rest, or direction. Now inertia, it is not a physical quantity, okay, but it can be represented by mass. Sorry, mass. Now this inertia, this is the representation in the linear form. When we talk about the rotational form, we get a moment that is called the moment of inertia, okay. We will not be talking about it right now, but just to mention it, okay. So you know what an inertia is right now. So what does the first law of motion state? Why is it called the law of inertia? An object in a state of rest or of uniform motion maintains that state unless and until acted upon by an external force, okay. This is called the first law of motion or the law of inertia. You can think about it in vector form in this, okay. So imagine there is this object, okay, one force is applying here, another force is applying here, and another force is applying here. So if F net is equal to F1 plus F2 plus F3, okay, if F net is 0, right, if F net is 0, then object will maintain that state, otherwise its state of motion will change. So if an object is moving with a constant velocity, right, and an external F net force which is non-zero acts on it, then the velocity of that object will change. If the F net, the net external force, it is non-zero, then that will change. But if it's 0, then object will maintain its velocity, okay. This is what it means by the first law of motion, right. Okay. Let's talk about the types of inertia. Why do I keep missing out on the A? Right. So there are three types of inertia. Inertia of rest, inertia of motion, and inertia of direction. Okay. The inertia of rest prevents the change of in state of rest of the object, right. The inertia of motion prevents the change in the state of motion. So inertia of motion, what it will do is protect the velocity of the object. So from the state of motion it can go to the change of rest, state of rest, right. The inertia of direction will protect the direction. Now why are there three types and how come an inertia of direction exists? So as you recall, I was talking about velocity. Velocity is a vector. It has magnitude and direction. So when we compare it to speed, if the speed change, if the direction of speed changes, it doesn't matter, the speed does not change. But if the direction of the velocity changes, the velocity will change, and that is why this inertia of direction exists. Okay, and that is why this inertia of direction exists. This inertia resists its change of direction. Okay. Okay. Let's talk about the second law. Second law. Now, as I mentioned before, a few things. I mentioned force, I mentioned momentum, I mentioned conservation of linear momentum, and I mentioned change in momentum, right? So when momentum changes, right, there must be a speed, a rate to it when it changes, right? So as that rate is there, depending on that rate, the force can change, right? That's all. Okay, what second law states. So you remember momentum was P is equal to mv, right? Change in momentum is delta P is equal to mv. Okay, delta P is equal to change in momentum, sorry, not delta mv. Why I erase that, I will just explain it now. Okay, now when we talk about the rate of change, okay, we are talking about delta P by delta T, and in this case delta T, it's so small. Delta T is what? Time. Sorry, I forgot to mention, it's time. It's the time in which this change is taking place. Okay, this change is taking place in this time. So when this time delta T, it tends to 0. Okay, tends to 0. That means this change in momentum is taking place across a very short period of time. That becomes the actual rate of change of momentum at that particular instant. Okay, so this is kind of instantaneous. So the rate of change of momentum at that particular moment is written as dp by dt. Now dp by dt, what does that mean? It just means it's a derivative of momentum with respect to time. So when we differentiate, let us think about P. Okay, so P is mv, as I mentioned before. So P is changing as a result of time. So therefore dp by dt is that. Now we are deriving it. So we get mdv by dt. Think about it. We have differentiated this, right, and we have gotten this. But is this correct? Mathematically, is it correct? Physics is a combination of science and maths. And we obviously we observe physical phenomena. But is that correct? No. Because if you do differentiation, we have a UV rule. And when we have a UV rule, one component is correct, but we have another component. It's called V dm by dt. Now in real life applications, in daily life, this component becomes 0 because mass does not change normally. But in situations when we are talking about the launch of the rocket, or when we are talking about the car itself, so they have fuel which gets used, which gets reduced to energy and then used. In that case, the mass of the car or of the rocket is changing, then this component comes into play, right? But if we are talking about you and me, the mass is not changing at that moment. It is technically, but not by that much. So therefore this tends to 0, the dm by dt component. Therefore we mostly talk about mdv by dt. Okay, so dp by dt, it becomes mdv by dt, right? Why did I explain all this? Because now we have to think about the second law itself. Okay. So what does the second law state? I explained the rate of change of momentum, right? So the second law states that the rate of change of momentum is directly proportional rate of change of momentum of an object. Let me just squeeze this in here. Is directly proportional to the force applied on it. Let's call it external, because this part is very important. It's an external force. It is directly proportional to the force applied on it and the change of momentum is in the direction of the applied force, right? I hope this is clear. Okay, this is important to write down like the first law. Okay, so we get F is directly proportional to dp by dt. Okay, now when we talk about SI units, F becomes equal to dp by dt, because in SI units K is found out to be 1. Okay, therefore F is equal to m dv by dt plus v dm by dt. But for day-to-day life we are going to ignore this component for now. Okay, later we will refer it when we will be using the full equation, such as in launch of rocket situations. Maybe not in this class, maybe another class. So if you note here dv by dt, dv by dt is nothing but, okay, so this becomes F is equal to mass times acceleration. Isn't this beautiful? Huh? Now in a real life situation, it is very important to understand the second component of this second law. The change in momentum is in that direction, which means that in some way the velocity has that direction in which the force is applied. Okay, kind of, not always, but kind of. So that was the second law. Okay, so we have F is equal to mass times acceleration. Now we will talk about the validity of the first law. Okay, the validity of the first law and the different types of frames of references. Now think about it. A person, he is in an elevator, right? And that elevator is moving upwards. Okay, but to him, he is in a state of rest, but he is moving. So there is an irregularity. The first law becomes invalid. Okay, so what is happening is, for him acceleration is 0. Now acceleration is 0, but there is a force which he can feel because he feels a reduction in his weight. That is why the first law becomes invalid. So when does it become invalid? This first law becomes invalid whenever there is a net force which is not zero on the object, which means there is a non-zero acceleration on that object, okay, because of this, right? What this means is, to balance out the equation we will have to use a pseudo force, okay. So before we move on to pseudo force, you need to understand, whenever there is an acceleration on the object, net acceleration, that means acceleration is not zero, this first law, the law of inertia, becomes invalid, okay. So then we will use a pseudo force. So right now let us imagine this lift does not have some mass, okay, we are just talking about the mass of this person. So the mass of this person is m, okay. The lift is moving upwards and giving the person also an acceleration of a, okay, but his mass is m, therefore a gravitational force is applied on him, which we call weight w, which is equal to mg, right? Now this is something which is very important, which will help you understand the concept of pseudo force. The acceleration is upwards, the person is in an accelerated frame of reference, okay, accelerated frame of reference. So to balance out these equations, we will apply a false force, that is mass times acceleration downwards, okay. It is a false force, we will use a dotted arrow, okay. So therefore, if you notice, when a lift moves upwards, you will feel like your weight has increased. This is the reason, because that person in that frame of reference feels that the weight has become ma plus mg, okay. W dash, also known as apparent weight, okay. This is due to the application of the pseudo force, right? All of this is just because of the frame of reference, okay. So as I mentioned before, he is in a non-inertial frame of reference. So in inertial frame of reference, acceleration is 0 and first law is valid. In a non-inertial frame of reference, acceleration is not 0 and first law is invalid. Depending on this, we have two types of frame of references, okay. Okay, coming to the last part of today's lecture, let's talk about the third law, the one which everyone remembers, okay. Third law, the law of action reaction. So say it with me. Every action has an equal and opposite reaction, okay. Simple. Let's write it down. Every action has an equal and opposite reaction, okay. What does this mean? What does this mean? We can take understand it through two examples. First one, there is this block, okay, and there is this person. He is applying some force, okay, some force on this object. It has a mass m and it is moving with an acceleration a because of that force. So that force becomes ma. Now this is the action. This is the action. Now as he is applying this force, as a result of it, a reaction force is also applied to him. Reaction force is applied to him, which has equal magnitude and direction is opposite, as you can see. So the force applied by the person is in this direction and the force applied by the block on the person is in the opposite direction, okay, but the magnitude remains the same. It is the mass of the object times the acceleration. Another situation, this block has a mass m, it's just lying on the floor, right? Now this block exerts a weight mg on the floor, but if you think about it, when you walk, you can feel that there is kind of an impact when you are walking or just standing, right? And as a result of your standing or walking, you feel tired, right? That is because this floor is applying a reaction force back on the block, on you, that is equal to that weight. This is called a normal reaction. Why is it called a normal reaction? Why is it called a normal reaction? Because it's perpendicular to the surface, right? It is perpendicular to the surface to which the force is being applied, okay? The weight is being applied, right? So as I mentioned this, we have a few characteristics of these action reaction forces. The first one is they are equal in magnitude. Second, they are opposite in direction. Third, they apply on opposing bodies, opposite bodies, let's just say opposite bodies. These are the characteristics of the action reaction forces, okay? I hope with the end of this, you are able to understand the laws of motion much better. Now this was the first part of laws of motion. Next time we will also cover friction, maybe banking, and a few other things, okay? Now today I'm not going to leave you with any questions. Maybe I'll add in a DPP later on, right? Thank you for watching and see you next time. Bye bye.